Accepted.
Okay, hello everyone, welcome. I hope you've been enjoying the conference. I'm super excited to be joining you today to talk about a topic that I'm passionate about, and that is observability and OpenTelemetry. Today the focus will be on instrumenting applications and the difficulty therein, and how to make it easier, especially in Java applications. First, a quick introduction. My name is Steve Flanders. I'm a Senior Director of Engineering at Splunk. I have been in the monitoring and observability space for more than a decade, both as a practitioner and on the engineering side, developing products in the logging, distributed tracing, and metrics space. I've been involved in the OpenCensus and OpenTelemetry open source projects, which we'll be talking about today, since the very beginning. And I'm currently in the process of writing a book called Mastering OpenTelemetry and Observability that will be coming out in the fall, and I hope you'll take a look at it. So I guess first, show of hands, how many people have heard of OpenTelemetry? All right, most people. How many people have implemented OpenTelemetry? Less hands. Yeah, see, that's common. So OpenTelemetry is very, very popular, right? But it hasn't been widely adopted yet. That's in the process of changing. So I just want to start by providing a little bit of a foundation about what OpenTelemetry is in terms of a project, and then we'll drill right into the instrumentation aspects. So OpenTelemetry is really an open source framework that makes it easier to generate, process, and emit telemetry data. You've probably heard of the 3 pillars of observability, being traces, metrics, and logs. OpenTelemetry provides a standard for those, what OTel calls signals. In addition, it handles other sources of data as well, including profiling, real user monitoring, etc. So in its root, it's what you install on your side of the environment to generate the telemetry data, but that's kind of where OTel stops. It does not provide an actual backend or an observability platform. Instead, it integrates with a variety of open source and commercially available backends. It's meant to be vendor agnostic. So what it's trying to do is standardize the telemetry aspect itself, not the backend that you end up using. In order to do this, it's made what's called the specification. This is kind of the open standard on which everything is built. That specification is made up of at least 3 major categories. The API and SDK, these are aspects that you actually use in your instrumentation. We're going to be talking more about that, so I'm not going to drill into it right now. And then there's a data aspect, which includes the data models, the protocols that are used, and something called semantic conventions. Semantic conventions we'll talk about in a second, but basically it's a normalization of metadata that you use on your telemetry data. Now from this specification, OTel actually provides reference implementations on top of it. There are several, but the 2 most major ones are instrumentation libraries. This is what actually goes into your application in order to generate that telemetry data. These are language specific, and all major languages are covered today. And then there's the data collection aspect, the OpenTelemetry collector being the biggest component there today. The collector can actually receive, process, and export this telemetry data. It can be deployed both as an agent or in a clustered fashion to aggregate data in your environment. We're not going to talk much about the collector today, but it is a very cool topic and something that I encourage you to go take a look at on the OpenTelemetry site. Now, the first question might be, okay, this is what OpenTelemetry is, but like what value does it provide at the end of the day? Now, I mentioned this open standard. Why does that matter? It matters for a couple reasons. One is it's completely open source and vendor agnostic. So OpenTelemetry is part of the CNCF, or Cloud Native Compute Foundation. It is not vendor controlled in any way, shape, or form. In fact, a wide range of community members contribute to it, including end users, vendors, cloud providers, and other open source projects. Now, that open standard then has implementations that you can take advantage of. You don't have to. You can actually make your own implementation based on the specification if you want. But the real value is what you can do with this data, what you get with this data. And that is data control and data portability. What do I mean? Well, if you're using this open standard, then it doesn't matter which backend or backends you're sending that data to. You can take advantage of it the exact same way because you're going to be sending it in the exact same format. That's very powerful. No longer do you have proprietary instrumentation in your environment and a proprietary data format that you're using, because that's hard to extend. If you want to switch backends, you have a different data model you have to deal with. It adds a lot of extra complexity, and it locks you into a particular vendor. The other aspect is data control. What do I mean by that? Well, Generating telemetry data, you want to control how much of it you're generating. Maybe you want to enrich it, add metadata. Maybe you want to filter it or sample it, remove some of that data. Maybe you have too much. Maybe it has personally identifying information and you want to remove some of that. All of that is possible with the OTel project, and you do that through configuration on your side. Now, of course, observability platforms will give you some of that flexibility as well, but again, they're going to have proprietary ways of doing that. OTel really is an open standard that you can take advantage of, and it can really future-proof your environment. The standard is also a superset of other standards. For example, this is the merging of two other open source projects, formerly known as OpenTracing and OpenCensus. Those were other approaches to kind of bring distributed tracing and metrics, a standardized format for them. There are logging formats as well that are supported by OTel. Prometheus is supported. So whatever like other common data models that are not like really vendor proprietary that you're used to, you can also take advantage with OTel. OTel can also be extended. So in the future, when new standards come out, they can be taken advantage of too. Now, why does OpenTelemetry matter? And I would say there are several reasons for this. One of the biggest is the Cloud Native Compute Foundation is made up of multiple open source projects. OTel is actually the second most active project in all of CNCF, behind only Kubernetes. I think that speaks to the fact that this is an actual pain point that end users and even vendors are dealing with, and that a solution is definitely necessary. You can actually confirm this by looking at DevStats. It's a Grafana dashboard that's provided by the CNCF, which actually shows you this data. And OTel's been in second place for years now, right? So it continues to evolve, continues to see active development. Now, in order for OTel to actually be beneficial at the end of the day, you need a variety of different observability backends to take advantage of it, both open source and commercial. And today, all major vendors support the OpenTelemetry standard. Now, they do that in different ways. OpenTelemetry actually has its own protocol called OTLP, stands for OpenTelemetry Protocol. And vendors or backends can choose to accept that data natively, or they may have their own format that they want data to be sent into, and there are ways to add what's called exporters into either the instrumentation or the data collection aspects of OTel components. And you can then send that to the vendor backend of your choice. So all major vendors support it today. The majority of them support native OTLP ingestion. Some have their own format. From an end user perspective, not only are we seeing adoption, we're actually seeing end users significantly contributing to the project. Instrumentation libraries, as I mentioned, are language specific. Some of those language instrumentation libraries in OTel have been completely contributed by end users, not by other vendors in the space. Even open source projects are adopting OpenTelemetry. So you might be familiar with Prometheus or Jaeger Tracing. Those are both CNCF observability platforms. Prometheus is in the metric space. Jaeger is in the tracing or distributed tracing space. Both of them support OpenTelemetry today. Jaeger actually got rid of its open tracing version of instrumentation and even their Jaeger agent in favor of OpenTelemetry components. Other open source projects, Kubernetes, Istio, Envoy, they all support emitting or exposing metrics that can be collected by OpenTelemetry components. And we're even seeing other like Apache-based products adopting it as well. So end to end, you're seeing broad support here. I didn't mention cloud providers because they're kind of in the vendor/not vendor space, but even they are adopting it. For example, if you're familiar with AWS CloudWatch, you can actually receive that data in OTLP format. So they expose that in an OpenTelemetry native way. Now, I'm not going to talk too much about the specification, but there is one important thing that we'll be using as we get into the instrumentation aspect, and that is around this data portability aspect and how that is possible. I mentioned it at a high level, but I want to drill into it. One of them is called semantic conventions. So metadata is very valuable on top of traces, metrics, and logs. Metadata would be things like key value pairs. Now, OTel provides semantic conventions, which basically normalizes the name that is used, the key that is used in that metadata. So there are different examples for different categories of data. For example, HTTP. You'll have like an HTTP.method or an HTTP.status code, right? This normalization gives you data portability because no matter what backend you send it to, it will have the exact same key. Even if you instrument different languages, you'll get the exact same key. This is very, very powerful because it enables some capabilities. For example, let's say that you instrument all the applications that you control, but you end up calling out to some other application that you don't control and you can't instrument. A classic example of this would be like a database. Maybe it's a third-party database or a cloud provider managed database. Well, you want to get some data about that endpoint that you're calling at the end of the day. And if you're using the OTel specification, this is actually possible. because all the outbound calls will be properly tagged with that information, tagged with that metadata. And so you can actually infer the service that you're calling. So you can have an application calling a database, as you can see in this example, and you would be able to represent that database and at least the telemetry data that your instrumented app is generating to call it. That wouldn't give you full visibility into the database, but it's better than no visibility whatsoever. So that's an advantage here. The other aspect of OTel is this notion of resources. This is kind of unique to OTel, but what it is at the end of the day is it's metadata specific to the infrastructure or the application itself. And it's kind of a pointer of where am I? Like where is this application running? This would include things like the host name, the pod or container it's running on, maybe the Kubernetes cluster, maybe the cloud provider region that you're in. And this is powerful too because it will allow you to slice and dice your data. So I can look at a trace or a metric or a log, and I can figure out like, hey, are all these happening in a specific region? Or are these happening on a specific pod or specific host? That helps with problem isolation, and that'll get you much closer to remediation of outages or availability issues that you have in your environment. Now, these concepts will be important later. That's why I want to cover them early, but let's drill right into the instrumentation aspect. Now, when it comes to instrumentation, there are clearly at least 3 signals that you're probably going to care about. I'm going to focus primarily on tracing, and usually I can demonstrate why. So, show of hands, how many people have instrumented an application with either metrics or logs before? Okay, that's the majority of the room. How many people have done it with tracing? Oh, that's pretty good. That's like a quarter of the room. That's better than I thought. So usually tracing isn't as common today, and that's because service owners usually own 1 or more applications, but they don't own the entire stack. And they may not necessarily care about how a request flows through the system. They care about how their independent service like operates. So they'll care about like metrics or logs that are being generated and whether it's receiving errors, but they won't look as much as upstream or downstream components because they may not be responsible for them. But tracing is very important, especially in distributed systems, because a failure upstream or downstream can actually impact your application at the end of the day. And tracing is important because it's the only signal today that actually has context and correlation built into it. And I'd like to demonstrate that. So here's an example of what could be a microservices application in your environment. As you can see, it's kind of like an e-commerce-based application. So you have like a front-end, checkout service, cart service, payment, what have you, right? So various different endpoints. Each rectangle represents a service or a microservice. And let's say they're all written in different languages. This is a polyglot architecture. Now, you can kind of see roughly how the flow of traffic would go. The arrows point who talks to who in general. But let's actually walk through a scenario of how this would play out. Let's say a customer is on your application, and they're trying to check out. What would that look like in terms of a flow through this system? So they would clearly hit the front end, because they're probably accessing it through a web browser or mobile device. And they would be performing a checkout operation. Maybe they're selecting the checkout button on the web page itself. The checkout operation needs to determine what's in your cart, so maybe it makes a call out to the cart service. And then it needs to perform certain operations like checking payment, currency, shipping, and also sending out an email confirmation, assuming that the operation is successful. That's a variety of different requests that might have happened as the result of clicking a single button in the UI. That would be an example of a transaction in your environment where it touched multiple microservices. You want a way of representing that, and that's what tracing provides. It does that traditionally through what looks like a waterfall view of a transaction. It could look similar to this. So that same exact topology, and I kind of walked you through with the circles, like which services were being hit, could be represented this way, where you can see again the front end, calling the checkout service, call cart, currency, shipping, payment, they're all here. And you can see roughly how long the duration of each of those operations took, and they're kind of a chained event. So the entire operation took 1.76 seconds. The bulk of it was the checkout place order operation itself, and then some calls are longer than others. You can actually enrich this with more information. For example, red metrics are very common for traces. That stands for requests, errors, and duration. You have a little bit of duration information here, but if there was an error, you could actually show it on this graph as well. This is one single transaction in your environment. But if you were running an e-commerce business, you probably have hundreds, thousands, millions of transactions a day. So you're not going to have one of these. You're going to have a lot of these. And really, it's the aggregate information about traces that really matter, because you can do some really powerful things with that aggregate information. For example, you can build a service map of your environment, right? You could build something like this. So what you see here is a topology of the exact same architecture that was constructed 100% from trace data, nothing more. So if you instrumented all your applications, you could visually represent them here. Here, the services are circles. Again, you can see the call paths. There's even some red metric information on here. For example, you can see the currency service has a solid red dot in the middle of it, indicating that it has errors. And you can see the slashed red for the front end and checkout service. These are propagated errors. They didn't originate in this service, but the error was passed back to it. This is valuable, right? Because now I can slice and dice my environment. I can figure out and pinpoint where problems are occurring. And let's say I wanted to learn more about the currency service. I could drill into it, and I could get a metadata breakdown of that particular service instance. So you were seeing earlier, like the semantic conventions, here's where they would come into play. You can see environment information, namespace, node name, all of that is available, and it breaks it down telling you where the errors are coming from. This could help with problem isolation. Because you probably don't have one currency service. You probably have 2, 3, maybe a dozen of them, depending on if you need to scale them out. Maybe they're deployed in different cloud provider regions because you want to have high availability. You don't know whether it's happening in dev or production or staging environments. All of that metadata can be used to slice and dice this. You know exactly which currency service or which ones are experiencing a problem in your environment. Now, full disclosure, what I'm showing you here comes from Splunk APM. That's irrelevant. Anyone that has tracing data can construct something like this, right? And with OTel data, again, you can construct a service map view, multiple backends support different ways of doing this. Now let's talk about OTel instrumentation libraries. I told you that they are language specific, and a variety of different languages are supported today, all the major ones. And on the server side, probably makes a lot of sense, Java, .NET, Go, Python, PHP, great. But beyond that, there are other types of instrumentation you probably care about too. For example, client instrumentation used for real user monitoring. This would include the web browser of the end user or the mobile devices that an end user is using. There's also instrumentation for that. Serverless is very common, especially in cloud-native environments. Serverless instrumentation is provided. The bulk of this, the ones with the blue header on the left, are all hosted within the OpenTelemetry project. And there are plenty of community-supported ones as well. That's with the orange banner on the right. For example, some of the serverless aspects are actually provided directly by the cloud providers themselves. GCP and Azure offer OTel support. They offer their own packaging for that directly on their documentation sites. Now, it's a single instrumentation library per language, and that gets you all the signals. So like, let's use Java as an example. I'm not going to install a Java tracing OTel library and a Java metrics OTel library and a Java logging OTel library like I do with most other instrumentation libraries out there today. I would install one OTel Java instrumentation library, and I can choose which signals I want to turn on or off. If I want all 3, it's provided. If I only want 1, I can configure it just to send 1, right? So you have flexibility and choice here every step of the way. Traces, metrics, and logs would need to be supported, of course, for you to take advantage of it. They are all supported. It's called stable in OpenTelemetry. That's the GA equivalent. That is all available for traces, metrics, and logs today. So you can easily rely on this, and many customers are using it in production. And then new signals are being added as we speak. Profiling is one of the newest ones that OTel is focusing on. Now, the next logical question is, well, how do I instrument an application, especially, let's say, I've never done it before? There's 3 primary ways in which you can instrument an application. Number 1 is manual. That means you're going to change your code. You're going to add additional code that is instrumentation library specific. In this case, it would be OTel instrumentation library specific. And you're going to manually add traces, metrics, and logs, or what other telemetry data you care about in your application. This is by far the most powerful way to add instrumentation because you have all the control. You can choose how much instrumentation you want to add, how much metadata you want to add. All of that is within your control. But it requires you to understand concepts like what are signals? What are these OpenTelemetry concepts? What's the API and SDK? And it requires you to make code changes. And if you're in a polyglot environment, that would be code changes per language, right? That's how you would get this. The other way of doing this is called automatic instrumentation. OTel is now referring to it as zero-code instrumentation, because that's what it is. Basically, this is adding dependencies and changing runtime parameters and just starting your application. You don't actually change the code itself. You inject things into the code at runtime, and that will automatically add instrumentation to your app. Now, this is usually a lot easier because I'm not changing the code, but it's also a lot less flexible. It will instrument what it can see, and that's it. If you want to change that, if you want to add more, you may be limited in what you can do because it's only what the auto instrumentation itself supports. There's also a middle ground. It's called programmatic usually, or library instrumentation is maybe another way to refer to it. This is where maybe dependencies, libraries, or frameworks that you're importing, they actually have OTel instrumentation natively included in them. That way, if you take that dependency, you don't have to instrument that part of the code. You just call the parameters of the library itself, and you get instrumentation included. Now again, that would only be for known libraries or frameworks. If it's not known, if it doesn't have OTel instrumentation, you couldn't take advantage of this. But it's a little bit easier. It's still manual, but it's less manual code that you need to add to your application. Finally, you can mix these to some extent, right? You can use manual and automatic at the same time. You can use programmatic and manual at the same time. You can't really use programmatic and automatic. It doesn't actually make a lot of sense. But in general, you can mix and mingle these as you see fit. And there are good reasons to do it. I'll actually demonstrate it with the API and SDK in just a second. This gives you kind of the most flexibility at the end of the day. All right, now in order for me to show you tracing, I have to explain some concepts real quick because they're super important, and this isn't a deep dive on tracing in general, but we talked a little bit about traces, right? Traces contain spans. Spans are individual like requests that are happening within a transaction. A trace is the entire transaction end to end, like what behavior, what services were called. In order for tracing to work, it uses something called context propagation. Now, context propagation can happen within your application, like calling different functions. It can also happen between services, passing contexts. For example, the trace ID would need to be passed between each of the services in order to stitch them together. Context propagation between services is traditionally done with HTTP headers. That's the most common way, but there are other ways as well. Also in tracing, it's very common to do filtering. It's usually referred to as sampling. This reduces the number of trace data that you are generating. The reason for this is because tracing can be extremely verbose. To be fair, logs can be very verbose too, depending on how you've instrumented them in your environment. But sampling is like, going back to that e-commerce example, if I have 1 billion transactions a day, do I really want to collect 1 billion traces that are all success 200 and took less than a second to resolve? The answer is probably not. What I care about are things like errors or like checkout operations that took too long. So I care about a subset of that data. Sampling can help reduce some of that noise if you wanted to. There are two primary ways to do sampling. Head-based means you make a sampling decision on the initial request. So for example, if I hit the front end service would determine whether or not it's going to create a trace for that entire transaction. And then there's tail-based sampling, which means wait for the entire trace to be assembled and then make a sampling decision based on some rules. Maybe, does any of the spans contain an error, as an example. Finally, we have OTel, and I mentioned that it has this API and SDK aspect. There's an important distinction here. They are different. They are not combined for a reason. The API are basically the public interfaces that are exposed to generate instrumentation in your application. The SDK is where all configuration occurs, also where processing and exporting would occur. The SDK actually contains the API, but you don't have to use the SDK. You could wrap your own SDK, for example. So decoupling the API and SDK was an intentional choice in the OTel project. All right, so I want to now show you. I'm going to start with a few slides, and then we'll get into an actual demo of how this is done. But first, I want to have a call out to my colleague, Jason Plum, who helped me put together this demo. This is my third presentation this month. Been super busy traveling around talking about OTel and OpenTelemetry, so he helped me create this example. And we had to create a specific example because I want to demonstrate all 3 different types of OTel instrumentation. And most of the examples in OTel today only show 1 or 2. They don't show all 3. So we ended up making something custom here. Now, I also want to call out that I'm not going to show you the actual OpenTelemetry demo environment. This is part of the OpenTelemetry project. Instead, I'm going to encourage you to go take a look at it. So there's something called the Astronomy Shop. It is the demo environment that OpenTelemetry supports. It shows all of the stable functionality of the OTel project. It actually provides a microservices application very similar to the one that I showed you. It is polyglot based. Every language is covered that is stable in OTel, and it shows you how instrumentation works and how the services behave with one another. I'm not going to use that today because we're focusing specifically on Java. In the case of Java, there are a variety of Java examples as well. There's a second link provided there that will show you all the different ways in which you can use OTel Java-based instrumentation. Unfortunately, none of those examples showed all 3 different ways in the same example. So we created something instead. But I encourage you to take a look at these. All right, so I'm going to show it to you first on slides because I think showing the code changes is easier here than going to the terminal. And then we'll jump into the terminal next. So what I have is a very simple Java web server. This is actually using the Amari open source library. So I didn't go with a Spring Boot application. I thought this might be a little bit better for demo purposes. But basically, it is a client and server running in the same JVM. So there are no microservices here. It's going to be one Java instance that's running at the end of the day. And it's going to do something very, very simple. So it's exposing a port. You can see here, I'm going to use an uninstrumented example. So there's no OTel instrumentation listed here. And we're going to start a server. And then we're going to run a client as well, right? So you can see the server builder here. It's exposing port 8123 and a /endpoint. And then we're going to run a client. Now the client is just going to call the server. Very, very simple, right? Client-server relationship here. Every 3 seconds. Just call out to it, and are we getting success or not, right? Very, very simple. The server is going to call a private function called calculate response, and that's just going to be a string, right? Hello DevOps 2024. Very, very simple. Now, I made this stupid simple just because instrumentation is a very complex topic, and I didn't want to show thousands of lines of code and try to decipher it live here, right? So here you can see just a traditional client-server model, and I want to walk through what it would take to add manual instrumentation, specifically tracing, to this example application. So let's do it. First, we have a bunch of imports. Irrelevant, but you can see the API and SDK are covered here, right? So there are like concepts in OpenTelemetry such as the tracer. There are things like the span builder. You'd have to add these components so you can actually call them within your code itself. And then you're going to need some generic way of setting OTel parameters. So you can see we're setting an OTel variable, and we're going to end up using it between the client and the server here. Now, we go back to our main function here, and we are going to set a service name. This part's very important. It's actually not required because the default service name is set, but I do want to talk about the importance real quick. Let's say I have 10 Java applications, and they do 10 different things. Do I want them to all be called the same thing? Probably not, because if I do, then all the telemetry data is going to look the same, even though the behaviors may be different between the services. So let's say I have a Java web server, and I have a Java middleware server, and they both are called Java. Then in the back end, whatever observability platform I'm sending that data to, if I didn't give it a unique name, then all the traces, metrics, and logs would refer to both instance types. That's not good. So I highly recommend that you at least set a service name for each of your services. I'm doing this within code. You can technically do it with environmental variables too. I'll show that in a second. But setting the name just gives me a unique instance of Java that I'm talking about. And then the SDK I mentioned is the configuration aspect. The good news is OTel provides a lot of sane defaults here. So I can just use auto configuration and it will set up just the default settings. The default settings would include batch processing, and it exports over the OTLP protocol. So it goes to localhost 4317 or localhost 4318, depending on if it's gRPC or HTTP. So this is nice because I don't have to make any changes here. But in production, like full disclosure, you're probably configuring the SDK as well. Because if you're in a containerized environment, like localhost doesn't mean what you think it means. If you want to send to an agent that's running on the host level and your container has a different localhost, then you can't communicate. You'd have to set the exporting destination as an example, right? So I'm not demonstrating that. I'm just showing you can configure the SDK. Now here's the more interesting part, right? So let's look at the client first. Okay, I have OTel. I've configured the SDK. I want to instrument the client call. I want to generate a span, basically. How do I do that? Well, I have to get a tracer, because the tracer is where my trace ID is going to come from and where I can generate my span information. And then before and after making my call, I have to basically generate this span. So you can see I'm building it, and I'm saying get the current scope of that. And then I'm still calling out to my server on the /endpoint like before. And then, very, very important, when I'm done, I have to end the span. So it won't end automatically, right? So I'm basically wrapping every single outbound call that I'm making with this span syntax. I then have to do the exact same thing on the server side. I need the server span as well. So here, I'm still doing the same thing. I'm grabbing the scope. I'm creating a span in between my call. I'm actually demonstrating one other thing with the server side, and that is setting metadata. So by default, if I'm using manual instrumentation, I will not get OpenTelemetry semantic conventions. That would be another import, another thing that I have to configure at the end of the day. But I can set my own, they're called attributes, that's the metadata equivalent in OTel. I can set my own attributes. So the example here would be, let's say I'm in a brownfield environment. It already has instrumentation. There are already semantic conventions that have been defined, like, for example, HTTP request path or request URL, and I want consistency in my environment, so I want to manually set the metadata that I'm using. That is possible within code as well. And it doesn't just have to be like these semantic conventions. Maybe you have business logic, customer ID, transaction ID, something else you want to tag within the trace. You can do that within your code as well. Now, of course, you could take advantage of the OTel semantic conventions for known endpoints, but your business logic, you're going to have to tag yourself regardless because OTel will not know about that. So here's an example of studying those attributes and, again, generating the span. Finally, I have a private function, calculate response. I want to generate a span for that as well. So basically, every single call now needs to be wrapped with this span syntax in order to generate the data that I care about. And we're just talking about traces. If you want metrics, you need to do more. If you want logs, you need to do more. So this is just for the tracing aspect of that. Long story short, I basically doubled the size of the code just by manually adding instrumentation here. And I had to know a lot of interesting things about the telemetry data that I was trying to generate. So let's kind of walk through that. Like, what else is missing? I didn't actually call services over the network, so there isn't actually context propagation in this example. If you wanted context propagation, you need to add that as well. You need to pass the headers of that trace ID so that it can actually stitch two different calls together. Otherwise, you'd have what's called a disconnected trace. That means I've generated span data in two different services, but I can't see that they're correlated because the trace ID is not the same in both of them. You don't want disconnected traces. You miss all the value of context and correlation. That's more code. I already talked about semantic conventions. We're not using them. You probably want to use them. That's more code. I talked about metrics and logs. You probably have metrics and logs that you care about. Even the return message, the response code, all these things you probably want to set. None of that is set in this example. I'm not returning any of that information. That would be additional code. Finally, there's resource information. You might remember this earlier when I was talking about the specification. I now know that, like, the client called the server. I know what endpoint it called it on. That's very valuable, but I have no idea what host this is running on. I have no idea which environment it's in, whether it's containerized or not. And so while I can tell you maybe something's not behaving correctly with the code, I can't tell you where. And with production environments and running like multiple instance types and maybe running in different regions or realms, that's critical information. More instrumentation you need to add. Long story short, it requires a lot of knowledge and a lot of code to do this manually. What does it actually require? Well, do you know what a trace is? Do you know what a span is? Context propagation, metadata? All those concepts need to be known regardless of whether you're using OTel or not. That's instrumentation library specific. Do you know the OTel specific conventions? For example, do you know the difference between a tracer provider, a tracer, and a span? Those are important concepts you have to add into your code. It's not that you can't learn this, you can, but it does require an investment to understand these concepts and make sure you're doing it correctly. You have to make sure that you end the span, right? Otherwise, they'll be indefinitely long. That's not valuable. That could have resource overhead issues. Metrics are very similar. Again, I'm not showing examples of that. Metrics have things like a meter, an instrument, and a measurement, and then you can do aggregations and roll-ups of that data. These are all concepts you need to understand when you're generating that telemetry data in your application. So an investment is necessary here to do manual instrumentation, but there's a lot of flexibility. If you learn these things, you can do anything in your code. You can generate as much or as little telemetry data as you need. You can fix specific availability or performance problems, or you can generically apply it to all the calls in your environments. I guess one caveat I would put is, if you are going to go down the path of manual instrumentation, make sure you don't instrument everything by default, because that's usually unnecessary and adds a lot of overhead to your application. You should be selective and careful about what you're instrumenting and why. At least calls between services is a great place to start. There may be reasons why you want private functions to be instrumented as well. That really depends on your business requirements at the end of the day. Okay, so how to instrument with auto-instrumentation. This is it. Just add 2 runtime flags to your application, right? We're going to add a jar file. It's called a Java agent in the case of Java. And we're going to set the OTel service name. I'm not touching the rest of the code. The entire uninstrumented app is exactly the same. Now start. You will get instrumentation. That's the difference between manual and automatic. This is really quick. I'm going to get a whole bunch of value. I will get resource information. I will get OTel semantic conventions. I will get context propagation. All of my calls for client and server will be instrumented. My private function will not be instrumented, though, because OTel doesn't know about it. So it only works for known calls, and it's kind of an all or nothing, right? Now I have to decide whether I want all the data that OTel is generating or whether I want to filter some of it out. but I don't have to go modify the code. I modify the runtime parameters and I start it up. Here's an equivalent example of how to do that using environmental variables. I just pulled out the Java agent and the deflag. These two things are 100% equivalent, right? But you can do this through environmental variables as well. This is an example that is specific to Java. There are equivalent ways to do this in other languages, but the semantics are different, right? This notion of a Java agent is Java specific. But there are ways to add auto instrumentation to a variety of other languages today, and you can get similar behavior where you don't have to manually instrument the code. Okay, so you can probably see the value. Let's actually see it in action at the end of the day. So I have an application here. We're actually using a demo environment that I have running locally here. So here, I have the code for all of those different environments: uninstrumented, automatic, programmatic, and mixed. Showing here, we have a build file, so we're using Gradle in this case. You will see that I have an uninstrumented, manual, programmatic, automatic, right? So I'm going to show you each different way of the code, and this code base is open source, so I can share out the link. I did make some modifications, so I will push that up before. So just heads up, it doesn't have all this up at the moment. So you can see kind of the differences between these, and then within the source directory here, so you can see where I am. I'm in source main Java IO OTel examples. You will see that I have the Java files: manual, automatic, mixed, library, and instrumented. Great. So let's look at uninstrumented real quick. Other than the imports, which I didn't show you on the slide, this is 100% identical to the slides I just showed you. 8124, run forever. We have our client, we have our server. There's no change here, right? So I'm just going to start this application up. I will do that by running the uninstrumented version. Here we go. And this will start the client server, and every 3 seconds, you should see that it's doing a request from client to server, and you can see the hello Devoxx pull in 2024. Very, very simple. Now let's go and just prove that this is real. So we'll go to the uninstrumented example. I'm again going to 8123 on uninstrumented. You can see it exists. And just to prove that I'm not like doing this like fakely, this is live. So if I choose a different endpoint, I get an error, right? So that works. I now have no instrumentation, but I have a running app, client server. Fantastic. Stop that. Now let's come over here and I will show you the differences between the uninstrumented and using auto instrumentation. The only differences are I renamed the public class and the endpoint. That's only because I'm trying to show you two different Java classes at the same time. I could just use the uninstrumented code 100% as it is, right? There's nothing OTel specific that you can see diffed between these two. Now I'm just going to start the automatic example. So let's run automatic. Starts up. And again, you should see a client-server relationship here. Every 3 seconds it generates. And right now, it's refusing to export data because I have not started my endpoint. But you can see it's actually already doing OpenTelemetry things. Great. So why is it erroring? Well, I need to start an endpoint to go receive this data. So I'm going to start a Docker container that's running Jaeger tracing. And I've actually configured it to enable OTLP, that is OpenTelemetry's protocol. And I'm exposing the ports, which are 4317 and 4318. That's it. I'm just going to start Jaeger up. Jaeger is running. Great. And now my errors here should start going away. And every 3 seconds, it generates a request. Good. No longer connection refused, so I am exporting data. That's amazing. Let's come on over now, and if I look at uninstrumented, it's no longer running because I'm not running that instance. If I go to automatic instrumentation, you can see it is running. And without making any code changes whatsoever, I can now go into Jaeger. I can go look at my automatic tracing example here. And here is data that is being generated automatically by OTel. You can see that it is calling the /automatic endpoint. I get a bunch of telemetry data here, including the port that it's running on, the HTTP status code, method, a whole bunch of useful information, even process information. Where is it running? It's running on my MacBook here, Darwin. You can see it's using Armaria, like I was talking about. All of this is provided automatically. 0 code changes to your application, right? And I'm just going to collapse these because it's a lot of information. You can even see that the client-server relationship, so here's the client call. That's also documented. What's missing? The call to the private function, calculate response. That doesn't show up here because the automatic instrumentation knows nothing about it, so it can't actually demonstrate it. But in literally seconds, I was able to instrument a Java application and prove that I can get telemetry data out of it. Again, this is just traces, but you can do the same thing with metrics and logs. All right, good. So now we've seen automatic. Let's go take a look at manual. So here we will diff uninstrumented with the fully manual. Forgot what I called it. Here we go. And here you can see that we had to wrap all the spans. Here's the span builder you saw earlier. Here's the wrapping of this, the starting and ending for the private function, for the client, for the server. Everything I showed you in slides, I think it's just a lot easier to see in slides than it is here. That had to change throughout my code base. So this is a manually instrumented example. I will go ahead and start that up now. So manual. Good. And I still have Jaeger running in the background, so we can export this data. And again, every 3 seconds, it's going ahead and exporting that data. Come on over, and automatic should no longer work. It doesn't. Manual should now work. It does. And if I come back over to Jaeger, I should now see a new manual tracing one. There it is. And here are my manually constructed traces from the exact same example I showed you in slides, right? So I can see that I have manual. You can see I'm not using OTel semantic conventions. I can see my HTTP request path that I manually added. I can see my request URL. I can see my private function because I went ahead and instrumented that private function. So calculate response does show up here. And I get some very basic like process information. But here I don't have like host name. I don't know what libraries I'm using, right? There's very basic information provided. I would have to add more manual instrumentation to enrich this like the automatic instrumentation provided, right? And then finally, I will show you programmatic instrumentation. So programmatic instrumentation just wraps a library. So let's diff uninstrumented with Java, oops, not Java mixed, with library instrumentation. Here we go. And so here, I'm actually just adding a decorator. So instead of wrapping it with a start span and end span, I'm wrapping it with our Maria decorator for each of my calls, and it creates the spans for me automatically. So basically, I've added custom code and Armenia dependency that is already instrumented with OTel. And as long as I decorate each of my function calls, it will show me that data in the backend automatically. So let's go ahead and show that one next. So this would be programmatic. Here we go. Running programmatic. Again, calling client server. That's great. Come over to programmatic instrumentation. It's running. Come to the Jaeger UI, and we now have programmatic tracing showing up. Programmatic instrumentation did wrap my call, did add the OTel semantic conventions, did add the process information, and I have my calls between the client, server, and my calculate response because that was manually added. I guess that's one thing that I did miss kind of demonstrating, which is with programmatic instrumentation, you can still add manual instrumentation. So programmatic by default would not have actually created a span for the private function. But because I'm using programmatic instrumentation, I can add manual directly to the code. I just added the same exact span wrapper call to my private function, and I can make it show up. That's an example of mixing programmatic with manual instrumentation. You can mix programmatic, you can mix manual with automatic as well. So 3 different ways of instrumenting your app, 3 different levels of complexity, 3 different levels of knowledge. Depends on which one you're kind of interested in at the end of the day to get kind of the value out of it. Now, I guess the last thing that I'll show you is like modifying this is pretty straightforward, right? So I think I have the library framework here instrumented. So let's look at our build hello handler. Let's say I want to enrich this. So you can see that there is no span data being generated here, but maybe I want to pass metadata between the instrumented calls that we have. You can see that there's already instrumentation here. I can simply do that by calling something like span, span current. I can say set attribute. And let's say I want to set an attribute of conference is Devoxx, right? There we go. So I'm just enriching, I'm manually adding a metadata tag to my data. And then I'm going to rerun this library programmatic instrumentation. Okay, done. And then I will come back and show that it is still working properly. Yep, that's good. Now what you will see is that in the Jaeger UI, if we look at programmatic data now, and we expand this example, we should see a new tag. Oops, did I actually refresh? If I get the latest tag, this one should hopefully show me the conference tag. Oh, there it is. It's on the client span, my bad. And now I added a new piece of metadata to the existing trace instrumentation. So simply and easily, I can actually extend examples too. If there's instrumentation in your app, right, maybe you're in a brownfield environment, someone's added instrumentation. If you want to make modifications to it, That's pretty straightforward. Again, if you understand kind of the concepts that OTel and the signal provide at the end of the day. So enriching it, redacting it, filtering it, sampling it, processing it in some way is all possible. Now, this is all instrumentation based. To be fair, you can do some of these capabilities in the collector itself. For example, the resource information, that's a great candidate to actually do in a collector running in agent mode on the same host as the application itself, because it offloads some of the responsibility from the application itself, thus reducing like any latency or additional overhead because of this instrumentation. In general, manual instrumentation is going to be lighter than automatic instrumentation. So while automatic instrumentation is a lot easier to get started with, it can be a little bit heavier in terms of resource utilization, just something worth noting. You'll have to test in your environment. But manual instrumentation requires understanding all the concepts. Okay, so what did we just cover here? What we covered is that instrumenting an application is work at the end of the day. You have to know what you're doing in terms of signals, in terms of telemetry data, in terms of concepts. OpenTelemetry is looking to normalize or standardize this information to make it easier to consume and then make it more flexible for you to transfer this data between different backends. Again, giving you choice. Maybe there's a reason why you want to send a subset of your data locally versus to a commercial vendor. Maybe you want to switch commercial vendors. All that would be possible. OTel again gives you flexibility between automatic, manual, and programmatic instrumentation, including the ability to mix the different instrumentation types. And as you can see, it's pretty easy to extend any examples that are provided to you. Now, there are a variety of resources that are available on the OpenTelemetry.io website that will help you drill into more of these. I talked about things like end-user adoption or vendors. There's links to that. I told you about the OTel demo environment and kind of getting started information. There's links to that as well. And then there's also instrumentation for Java. So if you want to do the manual examples or other extensions to that, that would be the second to the bottom link. And if you want to do automatic instrumentation, including other flexible configuration options for the Java agent, that's available as part of the zero code link here at the bottom too. Now, if you're interested in other languages, go ahead and take a look at the OpenTelemetry.io website. You can do automatic, programmatic, and manual and other languages as well. But OTel really is trying to provide an easy way here to instrument your applications to get value out of that data and to hopefully remove the vendor lock-in aspects of proprietary instrumentation and data collection. With that, thank you so much for the time, and I'd love to open it up to some questions.